Welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll be transitioning to turbulence. That is, we'll discuss the basics of turbulence and then move on in further classes of how these theories apply to computational fluid dynamics today. In the previous classes, we've looked at visualization. In particular, we had a whole module on visualization, which represents the post-processing, or at least part of it, phase of computational fluid dynamics. We focused on derived quantities. Today specifically, we'll move on to turbulence. We'll discuss a basic introduction of turbulence. There's no universal definition that's accepted on and regarding what turbulence is. We'll look at a number of examples, and this will help us define what turbulence is. We'll then look through the so-called basics of the Kolmogorov theory, which is one of the few analytical statistical solutions for turbulent flow, given some assumptions. We'll also look at a different class of flows, the boundary layers, which of course contain the law of the wall. We'll review this also. Finally, we'll look at different classifications of different types of turbulence models and how they might be transitioned to CFD. These are not necessarily CFD models, but those that came out of theory many years ago. Yet today, the turbulence models we develop in CFD usually fall into one of these particular categories. Let's get started. Turbulence has been studied for a long time. Here, we see one particular famous figure drawn by Leonardo da Vinci and is of course an illustration of turbulence. Here you might see some canal water coming through a square channel going into a pool or basin. It comes in laminar, comes around, and it swirls and swirls, and there's many eddies, and they break down to smaller and smaller eddies. From this, we can get some sort of qualitative figure or visualization of what turbulence might be seen from antiquity. Let's turn to our old friend Horace Lamb to see what he says about turbulence and how it represents one of the last great challenges in classical physics. Horace Lamb writes, "I'm an old man now, and when I die and go to heaven, there might be two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is turbulent motion of fluids. And about the former, I am rather optimistic." This was in his, of course, 1932 address to the British Association of the Advancement of Science. It's a little bit funny because if you look through a few different famous scientists and mathematicians' quotes, they've actually paraphrased Horace Lamb. This was done, of course, through the 1900s, and even today on occasion, as almost a joke, a tongue-in-cheek one. This shows the difficulty of the field, and many great thinkers have studied turbulence and have made no progress at all. It's easily a problem in classical physics which one might work on and make very little progress. On the right, you see a picture of Horace Lamb, where in previous classes we looked at another thing he's known for, which of course is the Lamb vector. It's hard to define turbulence, so we'll do this through some examples of turbulent flow and just discuss them and look at their quantities first. First of all, generally, turbulent flow happens in a three-dimensional regime, which has some viscosity. So, at large Reynolds numbers, the viscous stresses would normally become overcome by fluid inertia, and the flow might transition to turbulence. This is where laminar flow becomes unstable, and the theory of hydrodynamic instability might give us a way to understand these flows and their transition. This is a whole field in itself, that is, the stability of fluids. Now, the rapid variation of the field variables and their fluctuations will appear, and these motions become three-dimensional and unsteady. This is part of the transitional approach and process. There's also some critical Reynolds numbers which control the onset of turbulence. The critical Reynolds number is one particular non-dimensional parameter which must be overcome for turbulence to transition in certain types of flows, like, for example, a Couette flow, a channel flow, or a pipe flow. In other types of flows, perhaps temperature-driven flows, there'll be critical Rayleigh numbers. Some of these can be derived completely analytically, and we do this in my Navier-Stokes equations class, which is an elective for graduate students in mathematics, or of course, our field, aerospace engineering. Almost all turbulent flows become eventually some kind of problem for interest in engineers. On the right, we show a few examples from the book of Van Dyck. There might be clouds. The whole turbulent atmosphere, in fact, is turbulent, and it shows similarity to other boundary layers. You can think of the atmospheric boundary layer as a turbulent boundary layer. On the right, we have our old friend, the classic cylinder and cross flow, where the flow moves laminarly from left to right and comes around and transitions in this region because some critical values and instability forms in the boundary layer, and it separates in a large turbulent wave forms. This turbulent wake is very much like the one in the bottom, where this is like a wake of a ship, where we're looking overhead from a seaplane. You can see the same granular motion in the water basin is exactly seen and the same as in the flow near the bottom of the wake. The same vortex, von Karman type structures appear and instabilities. It's the same physics, but just at different scales. Let's now look at a few different definitions of turbulence from different sources so we get a particular idea of what a formal definition might be. Turbulence defined. Von Karman quoted G.I. Taylor. Von Karman, of course, was one of the founders of Caltech JPL. And G.I. Taylor writes, turbulence is an irregular motion which in general makes its appearance in fluids, gaseous, or liquids, when they flow past solid surfaces or even when neighboring streams of the same flow move past or over one another. This is just one particular definition, but note that G.I. Taylor defines that turbulence happens in fluids, gases, liquids, and note that includes plasmas. So there is turbulence in plasmas, and the whole field of plasma dynamics has, of course, people working in turbulence too. This is perhaps a little bit too restrictive of a definition because, of course, it doesn't really discuss what irregular motion might be. Turbulence is certainly an irregular motion. In fact, it's chaotic in a dynamical system in itself. It's deterministic in the sense that it can be described by the laws of probability and statistics. So we should also try and describe turbulence through statistical methods that were designed for chaos theory. Instantaneous properties of turbulent flows are extremely insensitive to initial conditions, but statistical quantities are generally not. This is an interesting statement and observation about turbulence. Recall our definition of the famous butterfly effect. This is where very, very small changes in initial conditions and equations of motion produce exactly the same solution at small times, but at large times they're completely different. This is the idea of sensitivity in chaos theory. Please recall that part of the class so you can review that. Of course, statistical quantities are generally predictable in turbulence, that they will be agnostic to these large changes in the dynamics of the temporally varying flow. For these reasons, it's probably and unlikely they will ever be able to compare a DNS, direct numerical simulation, of a very high Reynolds number turbulent flow with any type of carefully controlled experiment, because of course the initial conditions and boundary conditions are too sensitive. We will not be able to contain and compare the exact pressure time history, for example, in a turbulent flow. Another definition comes from Heinz, and they write, turbulent fluid motion is an irregular condition of flow in which the various quantities show a random variation with time and spatial coordinates, so that statistical distinct averages or values can be discerned. Let's look at some more famous definitions. Bradshaw adds to the Heinz definition that it would have a wide range of scales. What does this mean? That if we look at the scales of turbulence, the spatial scales and temporal scales, that they'll go from very, very large to, of course, very, very, very small. These scales might be examined through a particular analysis, and of course that's the Fourier analysis. We could take Fourier transforms of our turbulent field in spatial directions. A Fourier transform of, say, an x coordinate will result in a wave number, k sub x. So just like time goes to frequency, space goes to wave number. We would then look at the non-zero values of the wave number spectrum from the Fourier transform. We would see in a turbulent flow that a fully turbulent flow, especially, that all the wave number values would be non-zero through, of course, the whole range of scales of turbulence. This is a very interesting observation. Now, turbulence also contains the concepts and properties of instability and nonlinearity. So turbulence will develop an instability of laminar flow, and generally this instability will stem from the nonlinear terms within the Navier-Stokes equations themselves. Nonetheless, these instabilities, and you can see, could also be seen a little bit through instability analysis, linear, like you might learn in some controls classes as undergrads, or instability theory of fluids, like you might learn as a grad student. Now, there's so-called intersections of the fluctuations of various wavelengths. So if we can decompose our turbulent flow into different wavelengths via Fourier transforms or wave numbers, we'll notice that it's not a linear interaction between, say, the large turbulent eddies and the small ones. In fact, the large turbulent eddies and small turbulent eddies might very much have an effect on one another. And this is a nonlinear interaction. Why is it nonlinear? Of course, because of the nonlinear terms of the equations of motion. You'll note that we also see that in turbulence there's so-called vortex stretching in 3 dimensions. This does not occur in 2 dimensions. For example, imagine we have one of these little vortex filaments which we visualized in a previous part of the class. You'll see that these small little vortices could not stretch if they were only contained in 2 dimensions. They could not be elongated. This is why turbulence in 3 dimensions is very unique compared to 2 dimensions. In fact, many people today say informally that turbulence cannot truly exist in 2 dimensions just because of the fact that the vortices cannot stretch in a 3rd direction. So turbulence is inherently a 3-dimensional phenomena physically. Of course, mathematically, we can study turbulence in 2 dimensions and higher quite easily. The largest scales of turbulent motion carry the predominant amount of the energy. This can be shown by finding the energy spectra through Fourier transforms of a turbulent field. You'll notice that only very low wave numbers, that is, large scales of turbulence, contain the most energy. The least amount of energy is contained in the small scales. And of course, it's interesting that since most of the large scales contain most of the energy, that they would transport this energy through particular flows. For example, if you look at a turbulent jet, the very large-scale turbulent structures are carrying most of the energy. They're energetic and they're moving. The small-scale structures also contain energy, but much less. This can be shown mathematically and through measurement, through many different types of flows. It's something you should remember, and we'll see throughout our class. Now, the largest eddies will randomly stretch vortex elements, and by randomly I mean in a scientific sense, that it is predictable scientifically, and that they will compromise smaller eddies, which leads to a cascade. So what this means is that the largest scales of turbulence will slowly break down into smaller scales, and those smaller scales will break down into smaller scales yet. And every breakdown, the energy is transferred down the cascade. This is what we call the cascade of turbulence, that the energy from the largest scales is moving to smaller and smaller scales. Ultimately, the scales of turbulence will become so small that the terms of viscosity will be very, very large for those small scales, and the energy will be dissipated through the mechanism of viscosity at the tiniest scales, and this will be transferred mostly into heat into the flow, and of course a small amount of acoustic waves, if of course it is compressible, which truly all practical fluids are. Let's look at some more definitions of turbulence. There's certain statistical aspects of turbulence. We characterize turbulence by its random fluctuations. That almost always mandates the use of statistical methods for analysis. This is also the fact because, of course, the discrete or the temporally evolving properties are not predictable with CFT themselves. Only the statistical quantities are truly predictable, and they can only be compared with experiment in fully turbulent high Reynolds number flow. Unfortunately, the statistical methods prevent us from performing certain operations. As you imagine, with certain statistical quantities which we derive, we might lose some information, of course, about the full space-time solution of the Navier-Stokes equations. We also see and observe that turbulence itself is a continuum phenomena. It does not translate well into the quantum framework often used by contemporary physicists. This is why many people say it is the last great problem of classical physics which is unsolved, the understanding of the physics and mathematics of turbulence. This remains the last classical problem. By continuum, it means that the turbulence itself, this chaotic nature and beautiful scales of the evolving flow, will not appear at all in an environment where there's not enough particles where they can be viewed statistically as a continuum. This is what is meant. Tenikis and Lumley, in their book, write, even the smallest scales occurring in a turbulent flow are ordinarily far larger than any molecular length scale. This is another observation that they have made over their careers as experimentalists and theoreticians that helps provide evidence that turbulence is a continuum phenomenon. If we go back to the subject of vortex stretching, we'll note and observe that vortex lines in a turbulent flow will be non-parallel, and there's a strong vorticity within turbulent flows. Vortex stretching does not occur in two-dimensional flows, and therefore turbulence must be in 3 dimensions or higher. And the majority of vorticity within turbulent flow resides within the smallest eddies. And here's a figure from the book of Tennekes and Lumley, where they've shown maybe a boundary of a turbulent boundary layer as the black line, the average is the dashed line, the average of the boundary layer thickness, and delta is the boundary layer thickness. And in this little flow, they show particular little eddies which exist in the turbulent field. They do not exist in the outside part of the flow, which could be considered laminar. Here, the size of the particular vortice is written as the little L. That would be the length scale of one particular turbulent eddy in the flow. If this was in 3 dimensions, of course, it could stretch out of the page. In 2 dimensions, its stretching would be restricted. Turbulence will consist of a continuum spectrum of scales, ranging from the largest scales to the smallest that are possibly contained within the fluid volume or domain. The eddies within this spectrum will overlap and cause a cascade process. Remember, the energy will be cascading from the largest scales to the smallest, and the turbulent flows will always be dissipative, especially when you have larger viscosities. But even small viscosities will have dissipation. They're always dissipative, and the most dissipation of the energy of the turbulence will occur at the small scales, because of course they're most effective at removing energy. Of course, turbulence of any scale and size will likely, in reality, be dissipating some amount of energy. However, the majority of the dissipation of the energy occurs at small scales, where the viscosity terms and viscous effects are largest. We also note that for the largest eddies, that is, the large-scale turbulent structures, will likely mitigate through the flow and carry smaller eddies with them. It's not much like a very large eddy will contain tiny smaller turbulent eddies, and those smaller and smaller turbulent eddies will contain more, and they'll all be transported through the flow with the bulk motion of these large-scale turbulent structures. So it's the large-scale turbulent structures which are viewed to contain most of the energy and move most of the turbulent energy itself within its own eddy through the flow. So most of the energy in the flow will remain at these large eddies and will be more so persistent. By persistent, we mean that they last longer in time. The lifespan of a large turbulent eddy will last longer than the smallest eddies, which have a very, very small time scale. That is, that they exist and have a lifespan that's very small relative to the lifespan and persistence and structure of a large eddy. Next time you're driving down the street, try and look for a smokestack, and you might see large turbulent eddies coming out of it. These large turbulent eddies you can see with your eyes for a long time. Within those eddies are smaller and smaller structures. Try and just look for a smaller structure, and look at how long you might be able to track both the large structure and the small structure. You'll see almost always that the larger scale structures will persist, that is, they remain and live longer, if you will, than the smaller eddies. We'll also note that relative to a laminar flow, that diffusion is greatly enhanced in turbulence. And for this reason, many people still study turbulence. Turbulence is a mechanism to accelerate the diffusion of, say, particles within a field. So, for example, this might have a great application in inhalers. It would be very much beneficial to have an inhaler that has a turbulent flow into the lungs than one that is simply laminar. Our lungs themselves and the flow through our lungs is in fact turbulent, and this is beneficial because it enhances the diffusion of course oxygen and all our other gases moving through our lungs for our health to diffuse through the lungs, and it enhances their efficiency. In fact, if laminar flow only occurred in the lungs, then we would not be able to breathe. So turbulence is essential to many life systems, and our lungs is just one great example. Turbulence is usually dominated by large-scale energy-bearing structures, or in this case, we call them eddies, and they're responsible for the enhanced diffusion that carries most of the energy. Not only most of the energy, but of course, a lot of the diffusion effects. Smaller scale eddies are responsible for dissipating most of the energy in the flow eventually as the energy moves from large-scale structure to small-scale structure through the energy cascade. The mechanism of the viscous dissipation and the rate of dissipation will be proportional to the energy received from the larger eddies. So energy is conserved in the system in that it moves from large-scale structures down the cascade to small-scale structures and dissipates out into the field. Let's now turn our attention to one of the most complicated and celebrated theories that came out of the Soviet Union in the so-called Russian School of Mathematics and Turbulence. Andrei Kolmogorov, which was like one of the top 10 greatest mathematicians who came out of Russia, invented this particular analytical and statistical theory of turbulence. In particular, it applies to what we call homogeneous and isotropic turbulence. Homogeneous turbulence is turbulence where the statistics do not change with spatial position. Isotropic turbulence applies where the statistics of turbulence do not change with rotation. If we apply both these assumptions, we find homogeneous isotropic turbulence. Let's define and review the theory of Andrei Kolmogorov. We won't go through its derivation, which of course is only 4 or 5 pages in the journal Doklady, published by the Soviet Union. Here he views the smallest scales of turbulence and their estimation of scales, as their time and velocities and length scales, could be estimated through his advanced theoretical framework of fluid dynamics. He views and looked at experimental data and examined a so-called cascade process of turbulence, which transfers energy, that is the turbulent kinetic energy of the turbulence, from large eddies to small eddies. So he viewed that the largest scales of turbulence and their turbulent kinetic energy, which we defined in a previous class, and as you remind you, is the energy of the fluctuations of the flow, will move down from large eddies to smaller and smaller and smaller eddies through a large turbulence cascade which spans many decades at high Reynolds number. It will then approach the small scales, which will then be dissipated. This is the idea of the universal equilibrium theory, which states that the smaller eddies should receive energy from larger eddies, and then dissipate energy at nearly an equal rate into heat and acoustic radiation. The motion of the smallest scales will depend mainly on which larger eddies supply energy and the kinetic viscosity. Here we define, of course, this new term, kinetic viscosity, epsilon, and it'll go as the negative derivative of turbulent kinetic energy with time. So we're writing that the dissipation of the flow is nothing but the time rate of change of turbulent kinetic energy. It's that simple of a definition. The energy dissipating is equal to the rate as it is dissipated. Kolmogorov used a rather complicated theory and showed analytically the statistical theory of turbulence. And here are the 3 major results. If you want to talk more about how this theory was derived, then we should of course do it one-on-one in our virtual sessions or office hours. Here, Kolmogorov writes that the length scale, eta, will go as viscosity cubed divided by epsilon, the dissipation, to the 1/4 power. The time scale of the smallest eddies are the viscosity divided by the dissipation to the 1/2 power. And the velocity of the smallest scales will go as viscosity times dissipation to the 1/4 power. These represent, in any turbulent flow, the smallest scales of turbulence. The smallest scales of turbulence. And we measure their scales as length, time, and velocity. For example, if we can look at a giant turbulent flow at any particular time where these theory holds, that the smallest scales, the smallest resolvable scales of turbulence will be eta, which we call the Kolmogorov scale, length scale, the Kolmogorov length scale, the Kolmogorov time scale, and the Kolmogorov velocity scale. You will see these discussed in CFD and conferences on fluid dynamics endlessly whenever turbulence occurs. And in CFD, these 3 parameters are critical in every type of flow that we want to model and resolve. They are universally accepted. And of course, there's modifications to this theory today, which of course came out in roughly 1941. There's been modifications, and also there's another researcher named Obukov. We won't talk much about Obukov and Kolmogorov much more in a historical. You can see in this particular case, as viscosity is decreased, and viscosity is a very, very small number, we're cubing it. Think about how that affects the scales of turbulence. As viscosity decreases, of course, these scales, in their terms here, are going to become very, very, very small numbers. And of course, we're going to take roots of these numbers in some form and make them even smaller. And so for high Reynolds number flows, you can imagine that these values become very, very small relative to the largest eddy of turbulence. Generally, as the Reynolds number increases, and we'll show this calculation later, that these small scales and the large scales separate in order of magnitude at greater and greater values, which creates a humongous problem for computational fluid dynamics. We'll illustrate this in a later slide. Let's look at some implications of Andrei Kolmogorov's theory. First of all is an examine of the spectral decomposition of the energy. And earlier I discussed what wave number is. Now here we'll define wave number. Wave number will be kappa. And the corresponding wavelength for a particular wave number will be lambda. So the wavelength is lambda, and it will go 2 pi over kappa. Now, recall we have multiple wave numbers in a particular flow, from the smallest scale to largest scale. We can find corresponding wavelengths of each mode of the Fourier decomposition of the flow in terms of energy through this process. Now, a very simple and often used analogy for the wave numbers of a particular eddy can be used to find particular wavelengths or length scales of turbulent eddies. Let's now define the turbulent kinetic energy in a more direct way. Previously, we defined it, of course, as basically finding a kinetic energy of the velocity fluctuations. This is a very physical way to think about it. Perhaps a more elegant way for turbulence is to define it as an integration of the wave number spectrum. Here, TKE is turbulent kinetic energy. K will be kappa, the wave number. We also use small k for turbulent kinetic energy. So TKE and K is often used interchangeably. Here we have the energy spectrum of the wave number. And if we integrate the energy spectrum of the wave number of turbulence, then we'll find the total turbulent kinetic energy. Now the wave number spectrum of turbulence, the energy spectrum, is found through, of course, the Fourier transformation to the power spectral density, essentially, of the velocity fluctuations of turbulence. So we might write that the energy spectral density or energy spectral function E of k will be related to the Fourier transform of k through finding, of course, the energy of the flow via the method of power spectral density, which is nothing but using some Fourier transforms on the velocity field across space. Now, more important results, and we're not going to show every step of this theory, but we'll try and explain its implications, is, of course, based on the so-called Kolmogorov 1941 theory. And there's a whole history of this particular theory of when he wrote it, because as you see, it was written during World War II in Russia, which was not an easy place to do mathematical work. Now, here we will argue that the energy spectrum of turbulence, the E of k, which defines the energy of the turbulent kinetic energy at any particular wave number, will only depend on the viscosity and dissipation. This is an argument. The only two parameters are the viscosity and dissipation of the turbulent flow in any spacetime. So this energy mainly will flow and be contained within the largest eddies, which we observed previously, and we'll call those largest eddies L. Kolmogorov's theory can be used to argue that the dissipation of the turbulent flow will go as the turbulent kinetic energy to the 3/2 power over L. And you can see and fill in your particular dimensions to see that you do have a dissipation rate, which of course would be something like meters squared per second cubed. Using this argument, where L is the length scale of the largest scales and K is the total turbulent kinetic energy in the flow, this is just a dimensional argument, you can solve for K, of course, and you'll see that the turbulent kinetic energy in the flow will go as the dissipation rate times the largest length scale, L, to the 2/3 power. In most flows, you will find that the largest length scale is much, much, much larger than, of course, the Kolmogorov scale. This says that the largest scale of turbulence is many, many orders of magnitude larger than the very smallest scale of turbulence. So if you just take a ruler, perhaps naively, and measure a vortex at the small scale, you'll need a huge ruler and a different ruler to measure, of course, the eddy at a larger scale. In the turbulent atmosphere, of course, you have length scales, which can be, kilometers in size or larger, and you have Kolmogorov scales, which of course are on the order of centimeters or smaller, just as an example. And this one's not very high Reynolds number. Now, we can substitute in our estimation of the dissipation into the 1941 theory of Kolmogorov, and we can find these particular length scales from the previous pages. Here, look at these three length scales of space, time, and velocity. We can substitute these in these definitions and form these relations. We'll find that the largest length scale the integral scale, we call the largest length scale integral scale, L, divided by the Kolmogorov scale, the smallest length scale, will go as the integral scale divided by the integral scale divided by the viscosity cubed divided by epsilon to the 1/4 power. We can now rearrange these equations a tiny bit into this form. L times k to the 3/2 over L to the 1/4 divided by viscosity to the 3/4. How do we do that? Of course, we move the dissipation upstairs and make a substitution. Try it yourself. You'll see in this term we have a very interesting number. You'll see that this goes as a length divided by viscosity with some sort of velocity scale. This is very much the definition of Reynolds number. It is a velocity and a length scale, so it has units of velocity times a length divided by a viscosity term. This will go exactly as the Reynolds number to the 3/4 power. So now we write a little t here. That's the turbulent Reynolds number. Previously, you learned about Reynolds number from fluid dynamics and aerodynamics. That's Reynolds number applied to, say, just the global velocity of the flow and some large length scale like the diameter of a pipe divided by the viscosity. But this has nothing to do with that now. This is a turbulent Reynolds number, which is critical in the theory of turbulence and turbulent flows. So this turbulent Reynolds number will go to the 3/4 and go as L over eta. Let's rearrange these equations so that we can have turbulent kinetic energy in it. And solving for RET, the turbulent Reynolds number, we will find it is defined as k to the 1/2 L over nu. Of course, that's the definition. Why k to the 1/2? Remember, turbulent kinetic energy is units meters squared per second squared. So you would take the 1/2 power. So now we have a velocity of the turbulent kinetic energy, meters per second, times the length scale in meters divided by, of course, the viscosity. And it's a non-dimensional number. You see here what's interesting, if you equate Reynolds number, turbulence Reynolds number 3/4 to L over eta, if you increase the Reynolds number, then of course L over eta, that ratio becomes larger and larger. The message is, if the turbulent Reynolds number, or the Reynolds number of the flow, and the flow is turbulent, increases, the cascade will increase. That is, the ratio of the integral length scale with the Kolmogorov length scale will become bigger and bigger. This shows that the range of scales within the flow is dependent on the turbulent Reynolds number in a very simple and elegant equation. You can use this theory to start getting a physical and mathematical insight into, of course, the theory of turbulence. Let's look at some more simplifications and ideas from the Kolmogorov theory, which is critical for our module on turbulence modeling. First of all, remember, the energy cascade will transfer energy from large scales to small scales. Now, that does not say or mean that small scales cannot give energy to large scales. In fact, many people think they can, but that theory is less developed and accepted. Let's focus on the traditional theory that the large scales predominantly give energy to smaller scales. There's also an intermediate range of scales where there's a so-called equilibrium within the cascade, and this is called the inertial range, where the energy spectra of the velocity will depend only on the dissipation of turbulent kinetic energy and the wave number. Let's examine this plot on the right. This plot on the right, of course, is just a drawing to illustrate the cascade of turbulence. But if we put a hot wire velocity probe in, of course, a fully turbulent flow and found the wave number spectra through spatial Fourier transforms, we would find a plot that looks exactly like this. And this is a little bit universal. You'll find similar plots in almost every type of turbulent flow. Now, on the y-axis, we have E of kappa. That's, of course, the energy spectrum of the turbulence. The x-axis represents wave number kappa. Now remember, for low values of kappa or wave number, you will have very large scales, and for high values, of course, you have very small scales. You can see this for yourself with the wavelength lambda and, of course, the wave number kappa and its relation, which is the equation we showed on the previous slide. Now, if we plot our data, we will find E of k varies from the integral scale here, and we write L to the -1 because, of course, the units of wave number are 1 over meter as a value here, and it rises up and it peaks in this range, and then it comes down and it forms a slope, and it comes down and it dissipates. Here's the Kolmogorov or smallest length scale, written as 1 over eta. So this is the smallest scale of turbulence, this is the largest. This is how the energy varies as a function, of course, of wave number. in, of course, these length scales. So you can see most of the energy is contained in this region here, and we call this the energy containing region of the eddies. Beyond that, there's some inertial subrange, which represents a range between the energy cascading scales and, of course, what we call the viscous range. So we divide the range of wave numbers for this particular theory into three parts: the energy containing eddies, the inertial subrange, and the viscous range. Now you'll see for homogeneous isotropic turbulence that if we plot a log-log plot, that is, we plot log of log of E kappa and log of kappa, we will find a line which we can draw as a straight line through the inertial subrange. Now, on this particular figure, it's not really drawn to scale. For high Reynolds number flows, the inertial subrange will be the largest part of this figure. The energy containing eddies will be over on the left, and the viscous range will be way over on the right, and most of the figure will contain this inertial subrange. It's been expanded out for, of course, explaining the theory to students. This particular line has the form, which is found analytically by Andrei Kolmogorov, as the dissipation to the 2/3 times the wave number to the -5/3. This derivation, of course, is shown in his original paper. But it's a universal law. It's analytical and statistical turbulence. What does it mean? It means that the energy spectrum will fall off with increasing wave number as a particular constant for that particular Reynolds number of the flow. For a very, very high Reynolds number of the flow. This is the dissipation to the 2/3 times wave number to the -5/3. So dissipation will be constant if the flow is statistically stationary, especially if it's the isotropic homogeneous turbulence. And kappa will be -5/3, which of course gives the true slope. So this slope on the figure will be, of course, if it's log-log plot, -5/3 line with kappa. This inertial range exists exactly between 1 over the integral scale of turbulence and, of course, 1 over eta. Here C sub k is exactly a constant, and that is also derived by Andrei Kolmogorov. What a beautiful simplified equation for a very complicated physics problem. This was also derived completely theoretically before it was observed in experiments. So, much like Einstein derived the theory of, say, relativity before there was strong experimental evidence for it, Kolmogorov derived this theory before the experimentalists found strong experimental evidence of it. That is remarkable prediction. We've now explained the tip of the iceberg of Kolmogorov's theory of turbulence. That is, the wave number spectrum and the Kolmogorov scales of turbulence. Remember these. They will be critical later in the class when we're talking about turbulence modeling and resolving different scales of turbulence. Next, we're going to talk about the so-called law of the wall. The law of the wall is a semi-analytical theory or semi-empirical theory. It's a composite profile of the velocity of the boundary layer that is fully turbulent. For laminar boundary layers, the so-called Blasius solution exists, which is found through similarity solutions. In turbulent flows, no such analytical solution exists, and so we've piecewise put together solutions of the profiles of turbulent boundary layers. It's represented as an empirical theory, and is likely the most famous similarity relationship, at least in one particular region of the boundary layer, within fluid dynamics. And it's important you understand this because a lot of CFD turbulence models are derived to find, of course, turbulent boundary layers. And it's applicable towards boundary layer turbulence. Now, the streamlined velocity component near the wall will vary logarithmically with the distance from the surface. This is an observation, of course, found experimentally and then verified later with theory. And of course, the log law was found through some interesting research papers and PhD dissertations. Not one person can be really singled out as finding all these particular theories and putting it all together. It was actually a group of researchers over a course of time. We'll mention some of their names as we talk about it. Now, previously we talked about the energy cascade of Kolmogorov and his ideas, but it also applies to boundary layers, and in fact, all turbulent flows. We're not going to look at particular energy cascades of a boundary layer flow right now, but you'll see that energy cascades do exist and the same theories apply. Now, let's try and derive some sort of velocity scale of the turbulent boundary layer as a function of friction velocity. So for example, instead of doing Kolmogorov velocity scale, we'll do the so-called friction velocity. And this will go as the square root as the shear stress at the wall, that's tau sub W, mind you, shear stress at the wall, divided by the density at the wall, and take the square root. You'll see we have units of the square root of tau W over rho, that's shear stress at the wall divided by density at the wall, square root, will go and become units of meters per second if we're in SI at the wall. And so here's a non-dimensional parameter for velocity within a fully turbulent boundary layer. Here's an illustration of our problem, which we've explained extensively, and we've looked at boundary conditions and solutions before. To remind you, this yellow part's a flat plate. The blue or teal part is where the turbulent boundary layer exists, like we showed from Tenicus and Lumley, and we have a uniform inflow from left to right. Let's not worry about boundary conditions for the CFD. Let's talk about the physics and the mathematics. Here, the turbulent boundary layer, of course, creates this profile as it progresses downstream. There's the so-called law of the wall, which will dictate the format or profile of this particular boundary layer. Now, the friction velocity will represent the velocity scale, which is close to a solid boundary. This is the velocity we just formed. Now, let us postulate that a mean velocity gradient, partial u, partial y, that's the derivative of the velocity in the streamwise direction with respect to the normal direction from the wall, will be correlated as a function of the friction velocity, viscosity, and y, the distance from the wall. So y is the distance from the wall, nu is the viscosity, and u sub tau is the friction velocity, which we just defined. So we are defining this relationship. We are postulating that this is true. So we'll say partial u, partial y, and capital U here is the mean velocity in the streamwise direction. That's the direction of the flow relative to the wall with respect to y. So partial u, partial y will go as the friction velocity divided by the distance of the wall times some arbitrary function, which we don't know yet, of uty over nu. This is a postulate. Let's see how it works. We'll say that f is some universal function. And from many experiments of turbulent boundary layers at different Reynolds numbers, distances downstream on the plates, different distances from the walls, we can look at all this data that is fully turbulent, and we can find that it does indeed have a universal function. And this universal function will have the form here, 1 over kappa. Now here, kappa is not wave number. In the context of boundary layer theory, it is actually constant. It's the so-called von Karman constant, which we'll discuss in a second. And this function will go as 1 over kappa, I haven't finished yet, as the friction velocity times y over nu goes to infinity. So as friction velocity increases, or distance from the wall increases, or viscosity decreases, this term goes to infinity, which is the argument of f, and it'll go to the constant. So you see, for small values of the argument of f, u tau y over nu, then of course it won't necessarily be this particular constant, but it will have a particular form. Now, looking at the experimental data and its collapse according to this theory here in our postulate, we'll see that f mainly varies as what? It mainly varies as the friction velocity and y. We're saying, well, viscosity is relatively constant in most low-speed flows. Of course, we would have to modify this theory for higher speed flows, but you'll see it still works wonderfully. Anyway, f will vary with u tau over y because viscosity is relatively unchanged. So it only depends on, perhaps, viscosity, as viscous effects will dissipate far from the surface. So we won't worry too much about the viscous term relatively to these other terms, ut and y. So we propose this particular relation from the first equation and put in a functional form of f, given the boundary condition that it asymptotically approaches 1 over kappa for large uty over nu, its argument, and that we observe experimentally that it mainly varies for smaller values of uty over nu with uty. There's really only one functional form. Well, actually, there's a few others, but one is really the one that's universally accepted, and most evidence points towards its true, because of course there's multiple choices for what f might really be. It will turn out to be as the mean velocity at some position y, at some position x on the plate, divided by the friction velocity, will go as, see, we take mu tau and divide both sides by it, as 1 over kappa times the natural log of the friction velocity times the distance from the wall divided by the viscosity plus a constant. So you see, this form came out of something like an integration of the previous equation, because we had partial u, partial y. Now we have u, and dividing both sides, and we get a constant of integration. This, of course, is in a logarithmic form. So what does that mean? It means that just like the inertial range in a fully turbulent flow from Kolmogorov, there's also some range of the velocity which goes as the log as the distance from the wall at a particular ut and viscosity. For any particular x position on the plate, utah would be constant. That's, of course, related to the shear stress at the wall, right? And the density at the wall. So y would only be increasing. So u is really a function of y in this particular equation for some particular values of u2 and viscosity. Now it turns out that we can derive and find constants for this particular equation given certain conditions of the fully turbulent flow and assumptions. The constants turns out to be dimensionless from dimensionless integration and experimental verification that c is approximately 5 right here. Kappa will be 0.41, which is derived theoretically from the theory. So now we have what we call the law of the wall, that the velocity in a fully turbulent boundary layer away from the wall varies logarithmically, which is a key fact in the theory of turbulent boundary layers. Let's now look at how the velocity varies in a fully turbulent boundary layer. Here we illustrate this through the so-called law of the wall. And this is what we're talking about when we refer to law of the wall. It's, of course, the composite plot of the turbulent boundary layer velocity with respect to the distance from the wall. Now we'll define two non-dimensional numbers. The first is u plus, and u plus will go as the velocity, which is the distance from the wall, divided by the friction velocity, which we derived 2 slides ago. We also non-dimensionalize the distance from the wall as y plus. Y plus will go as the friction velocity times the distance from the wall divided by viscosity. This will give us our non-dimensional distance from the wall. Now, it's very much possible to plot u plus versus y plus. When we make these types of plots, u plus versus y plus, we call these the so-called inner coordinates. These are the inner coordinates of the turbulent boundary layer. Outer coordinates are simply when you plot u versus y. Now, in the inner coordinate framework of u plus and y plus, right, which are dependent mainly on the friction velocity and the distance from the wall, because u is only dependent on the distance from the wall at its local position x downstream from the leading edge of the plate, we can plot what we see as a linear log plot. The x-axis is y plus, which is the distance from the wall. For example, here we have a y plus distance of 10, 100, 1000, 10,000. The y-axis will be plotted in a linear framework as u plus from 0, 20, 40, 60. So u plus of 0 means the velocity is 0. Y plus of 1, of course, means here, if it's a log plot, that we are exactly y equals 0. Check it out for yourself. So by definition, if we hold the no-slip condition to be true, then the velocity of the wall will be 0, and of course y plus will be 1. If you create your own u plus y plus values from, say, experiment or CFD, you'll have to probably make sure that u plus and y plus have this value of 0 and 1 respectively. Otherwise, you know that you've made a mistake. Now, in this particular graph, there's 3 particular regions of the flow in any turbulent boundary layer. We call these the viscous sublayer, the log layer, and the defect layer. Typically, we have shown in the previous slide on 16, the final equation, that u goes as the log of course, y. That's what's shown here in this region where my cursor is moving, between, say, in this case, y plus of 10 and 1,000. This is what we call the log layer, and refers to, of course, the law of the wall, because it's a log layer region. Now, very close to the wall, between the wall itself at y plus 1 and roughly 10 to 12, u plus is exactly equal to y plus. Why is that? Because, of course, it is really truly a laminar type flow in this region. That is, the viscous effects in the viscous sublayer are dominating the flow, and we'll find this universal nature of the flow that u plus equals y plus. It's a wonderful collapse of the data. Beyond the viscous sublayer region, we have many, many, many decades of y plus. That is, in a higher Reynolds number flow, the distance between, say, the bottom and top of the log layer will increase, increase, and increase. And of course, the viscous sublayer and the defect layer will be relatively small compared to the log layer in a very high Reynolds number turbulent flow. You'll see that it goes very much this line as u plus is 1 over kappa, the natural log of y plus plus c. That's what this dashed line is here. and you'll see it exactly corresponds to this particular set of data. This is why they call it the log layer, because this equation, which we derived from a little bit of dimensional analysis and theory, exactly predicts the log layer region. That's fascinating and an amazing find. Finally, out there, you'll see at very large y plus, we get a u plus value of, say, maybe 35 in this case. And that would correspond, of course, to the u value divided by friction velocity, where u value at a large y plus going to infinity would be, of course, just the ambient velocity, like the velocity of the aircraft, the undisturbed air. So this must match and have a zero derivative with, of course, the far field velocity. So the defect layer is the region of this profile between the log layer and how it matches with the ambient velocity. You can see there's a large change and variation difference between the log layer equation, of course, the defect layer in reality. So if we take any fully turbulent boundary layer and find these parameters and collapse them into this profile, we will always see, if we follow the assumptions of this theory, that there's this perfect log layer which matches our theory, and of course this viscous region with u plus equals y plus, and then some defect layer. So if we want to construct a universal theory for turbulent boundary layers, that is a composite profile which combines empirical and analytical work, to collapse all this data from a wide range of experiments, and we'll have to modify it some. That's what we'll do. So we will assume that the velocity in the viscous sublayer depends on u, tau, nu, and y. We can write an equation like this. And we see this from experiments to justify this choice. The velocity in this viscous sublayer goes as the friction velocity times some function of y plus. You can imagine where this is going. We already know the dimensionless form of y plus from our choice. This is the form of the law of the wall, of course, which we just showed. Now, experimentally, you'll see that some velocity data correlates very well with the so-called velocity defect law of Clauser, who proposed how the defect layer changes relative to the log. So we need to take this theory and match this whole profile to construct this composite profile, which would be the black line, which would correspond to experimental data. So Clauser defined this type of equation. He said u equals the undisturbed velocity far outside the boundary layer minus u tau times some function g of eta. And here he defined eta in the so-called coordinates here, which are like another dimensionless form. Here he writes y over delta. Here, this is considered to be like an outer coordinate. Why? Because delta is seen as the thickness of the outer layer. That is the larger length scale than, say, like, Kolmogorov scale. So now we're faced with two different scales. The first, of course, is nu, the viscosity divided by the friction velocity, which is basically like a length scale now, and delta, which is another length scale. These are two scales, the so-called inner scale and outer scale. It's that simple, as shown by the definition of Clauser. So you can see here's another person involved in the development of these equations. Note that the boundary layer itself was proposed way back in the early 1900s by Prandtl, and about 50 or 60 years later, it took Clauser to come along and close the composite profile theory, using what we're showing here. Interesting history. Nonetheless, you'll see that there's a large disparity in size of the scales of the inner and outer length scales. Nu over friction velocity u tau is much, much smaller than delta. So if we want to have a continual velocity variation in our inner coordinates or outer coordinate plots, then of course there must be something that's changing between the two scales. And we'll call this an overlap region, which must exist between these two types of profiles. That is the Clauser or defect layer and of course the log layer. How do we match them? Well, of course, Clauser went along and he proposed the following equation. He writes the friction velocity times some function of y plus will be equal to the ambient velocity minus the friction velocity times g of eta, which of course is this scale. Y plus is inner length scale, a function for f, and g is eta, another function of the outer scale. We need to somehow try and match these. Now, for values larger than y plus and less than eta, which would be, of course, in this region, because it's much larger than y plus and much smaller than delta, or eta. This is 10 to the fourth. And of course, y plus small value is 1, so 1,000 is much larger than 1, and 1,000 is much less than 10,000. This is this type of region, an argument. We will find, of course, a matching type of equation by differentiating this equation with respect to y. And we'll find the following equation. The friction velocity squared divided by viscosity times the derivative of F will be equal to the negative friction velocity divided by delta of G, derivative G of eta. And of course, this should exist. We're matching the derivatives so we can match the slopes in the composite profile. That's the goal. Now we can multiply this equation through by y over u tau. And we'll find this particular equation. Y plus f prime equals negative eta g prime for this range of y plus and eta, which we just identified. You'll see that there'll be a wide separation of scales, and we can regard y plus and eta as independent variables. The only way a function of y plus can equal a function of eta will be for both to be equal to a particular constant. It is the only way to do it. And so this is a very interesting matching asymptotic analysis of mathematics to find these particular constants. So we will find and deduce that y plus f prime of y plus will be a constant, which is we will set to 1 over kappa, which is a careful choice from the original log law theory on slide 16. Try and look and make that argument yourself. This will imply, of course, that we can write that f itself, if we take the integral of both sides, will go as 1 over kappa, the natural log of y plus c. So, in some sense, by making this choice, we recover the log law itself, which justifies some of these arguments which we observe experimentally from the log layer region. For this particular region, the defect layer, matching these equations. That's excellent. So we still have to form a defect region. So this is what Coles did based on Clauser's viewpoint. And he wrote that a velocity defect region can be formulated from a departure from the logarithmic region to form a composite profile. A composite profile here is an equation, a closed form empirical equation based on this analysis for the entire turbulent boundary layer. Let's look at this particular statement, a departure from the logarithmic region. That's right here between 10 to the third and 10 to the fourth y plus. Here's the original log layer, and here's the departure from it. This is why it's a defect layer. It's defecting from, of course, the log layer to match the ambient velocity. This is what we see in all high-speed, fully turbulent flows. Beautiful. Let's look at the composite profile. Now we can rewrite it. Before, just the log layer itself had u plus of 1 over kappa of the natural log of y plus c. We now add in the Coles defect wake strength parameter, which is an entire term in this case with a constant. Pi, capital pi, is the actual constant. We'll have 2 pi over kappa, which is where that constant's coming in here, right here. We'll go as sine squared pi y over 2 delta. So this form, sine squared, is actually a bit of a choice. And that's used to match the log layer, of course, continuously with the ambient flow. Here, pi is a constant, and it can, of course, be varied to match particular types of flows, depending on Reynolds number. It's not like a universal constant like kappa or c, which is rough 5, 0.41. C is about 5, which might vary a little bit, and pi, which will vary a lot depending on the Reynolds number of the flow. So, it'll depend on delta, which is the outer scale, and the boundary layer thickness. It'll vary pi, and it'll also vary with pressure gradient. So pi, in this case, capital pi, it's not 3.14, it's just a constant, will be approximately 0.6 for constant pressure gradient flows. That means the pressure is not varying in the turbulent boundary layer very much as you move downstream. So let's examine Coles' original figure on the bottom of page 20. It's its so-called wake strength parameter, which is showing in the composite equation for particular pressure gradients. The pressure gradients are written non-dimensionally as a function of beta. So beta is non-dimensional pressure gradient. Beta 0 is no pressure gradient. You can see around 0.6 here is the value. With increasing pressure gradient, of course, the value of pi will be increasing. So to find the right composite profile, you would actually have to change pi in the composite in the equation to find this profile. Nonetheless, we've developed a composite profile equation for the whole flow. You might be wondering why, as a practical user of CFD, you might care about this at all. Well, we'll be talking about that at length in later classes. But as you imagine, if we wanted to resolve the turbulent boundary layer to find the correct velocity profile, which would then be used to find the correct drag. is, of course, the derivative of the velocity at the wall dictates the type of wall shear stress quantity we will find, which dictates drag. So this means we have to have enough grid points in the region of y plus less than 10 to resolve the viscous sublayer. If you don't, in traditional CFD analysis, you won't be able to find the correct drag. So this is an interesting way of analyzing a turbulent boundary layer with no CFD to estimate the number of grid points near the wall. We will talk more about this. Let's now turn our attention away from the two most important theories of turbulence, in my opinion: the boundary layer flow turbulence, composite profiles, and the beautiful and elegant theory, which is analytical, of the statistical theory of turbulence from the Russian school of academician Andrei Kolmogorov. We'll now look at a subset of turbulence model classifications. First, of course, there's algebraic models. These are models based on the so-called mixing length hypothesis. This is where we have some particular length scale. These are also called zero equation models. We will look at these in this class and upcoming classes. Another classification is the so-called one equation models. Now, most one equation models use one particular differential equation in addition to the set of Navier-Stokes equations, which are modified. Most one equation models use what we call an eddy viscosity. An eddy viscosity is a modification of the traditional viscosity term. One equation models are very prevalent in computational fluid dynamics today. Finally, another classification of major types of turbulence models are two equation models. That means we're using two additional differential equations relative to the set of original equations to model the turbulence in the flow. These will typically be used to model turbulent kinetic energy and dissipation in the flow. They represent the first complete models of turbulence. And of course, the first complete model of turbulence was also written by Andrei Kolmogorov. What an amazing contributions. Anyway, this will use two different equations to close the set of equations. And I mentioned the word closure, which of course is going to be a topic for next time. We're going to look at, in this class, these three types of models at length because they represent the workhorse models, if you will, of a certain type of flows to model turbulence in computational fluid dynamics. We'll talk about the reasoning that we perform these models in future classes, but for now just realize there's three, and they can be broken down by the number of additional differential equations. You might also say, well, are there more turbulence models that use more differential equations? And the answer is yes. Sometimes people can use up to 6 or 7 or even more additional differential equations beyond the Navier-Stokes equations to model the turbulence in the flow. You can see this is an entire field in itself, and some people spend their careers trying to create better turbulence models. There's other kinds of turbulence models too, which we'll also discuss in future classes in this module. For example, large eddy simulation, which takes a little bit different approach than the ones listed on this slide. There's also what we call stress transport models, and these might transport the stress tensor of the turbulence. And this uses multiple difference equations too. They might be called second order closures or second moment closures. We'll look at these in this class. Finally, we'll spend a whole class on direct numerical simulation, and what is becoming very popular today in research and industry, which is a little bit different, is called large eddy simulation. This is the idea that we're going to directly model the largest scales of turbulence in the flow with, say, the Navier-Stokes equations. And all the smaller scales, because they have some universal behavior, according to Kolmogorov and colleagues in the School of Turbulence, that we will model them. Of course, we know something about their statistical behavior from, say, law of the wall, or perhaps something about the cascade of turbulence in a homogeneous isotropic flow. There's many variants of LES, and it'll be fun. You'll see the major equations and how they're solved in CFD. The bottom line, if you're a user of CFD, is that you have to choose the correct turbulence model for the right job. And you have to know something about the flow in advance, much like the composite profile of a turbulent boundary layer, to set the number of grid points and even choose a particular turbulence model to model that type of turbulent boundary layer. It becomes very complicated, and you can spend a lot of time just on these subjects. In fact, typically in a graduate school, there's a whole class on inhomogeneous turbulence and its modeling. Nonetheless, this is not an all-encompassing list, and there's many variants of turbulence models and modeling being performed and created today. It's an active and very difficult field of research, and part of its difficulty, of course, comes from the fact that turbulence remains an unsolved problem. Let's now take some time to look at some examples of turbulent flows, just to get a better idea of them. And of course, many of these are from the Book of Van Dyck. Here's a turbulent flow which transitions from a laminar flow through a transitional region into fully turbulent flow, which then breaks down again. This is generally a transitional flow because it goes laminar to turbulent and decays very fast. It never really forms fully developed turbulence. Fully developed turbulence can only be classified as a wave number spectrum of all known zero components between, of course, the Kolmogorov scale and integral scale. Here's more examples, which we showed in the beginning of the class, but this is a typical airfoil. The flow moves from left to right with streamlines of smoke. There's the airfoil itself. The flow remains attached on both sides, and a turbulent wake forms in the wake of the airfoil. If the airfoil goes to a higher angle of attack, you can see right here, of course, that a large turbulent wake forms. You can see the turbulence and the diffusion of the smoke. Recall earlier I noted one physical phenomenon of turbulence that is excellent at the dispersion of particulates. In this case, these smoke streams are being dispersed highly effectively in the turbulent regime. That's how you partly know that there's probably a large region of turbulence there, because it's efficiently mixing the turbulence, efficiently mixing the smoke particulates. Look at how this is not the case in the laminar flow. If we choose one particular streamline and it goes downstream, it's not broadening at all. The diffusion of the smoke particulates along these particular lines is so slow that it's not even broadening in the high-speed flow. So a laminar flow is very inefficient at, diffusing particulates of smoke relative to turbulence. This can be illustrated in this case. It's very interesting to me. Here's a backward-facing step. You can see this beauty of turbulence forming behind the step. Here the flow is laminar. Down near the step, backward-facing step, if you will. Actually, it's a hump, excuse me. The flow separates, and you see a large turbulent structures forming here, shedding downstream. Here's the kitchen example, which I talked about earlier in the class. You can always go into your kitchen and turn on the faucet and watch the so-called laminar flow from the faucet come down if it's just barely on, and you can open up your faucet more and more and see the flow coming out of the faucet transitioning and then going to turbulence. Try it in your kitchen. It's a fun experiment. Then you can, of course, see in the basin, there's all kinds of transitional and surface waves and turbulent flow all within the water of the basin. It's very interesting. Here's a typical smoke example, which everybody loves. On the left, we see smoke coming up. It's laminar, it's transitioning and becoming fully turbulent. Now, if I go into this flow and put a little probe in it to measure velocity, I could find the energy spectrum, and you would see it have somewhat of a spectrum which, like Kolmogorov predicted. It's very interesting that happens. We can put a spoon in the smoke stream and see the smoke come up and go around the spoon, and it forms this turbulent wake. So this is another visualization of turbulence. Here's just a higher Reynolds number and closer view of that turbulent wake. You can see all these beautiful structures. And in this class, I talked a lot about what are large-scale structures and small-scale structures. And this is a great example because it's a relatively low Reynolds number flow. And so the turbulent cascade isn't very large. That is, the distance, the number of decades between the integral scale and Kolmogorov scale are very small. I might view maybe this is one large eddy. Where my cursor is, this might be a smaller eddy. And if I look in here, I can see a very, very small eddy. So this might be on the order of what is closer to the Kolmogorov scale or small scale turbulence. And it would dissipate into heat and acoustics. And this large scale is like the integral scale or the largest scale of turbulence, and that carries most of the energy. So you can see as it comes up, the scales of turbulence are transitioning from laminar to transitional and become larger and larger to integral scales, which then become fully three-dimensional turbulence and break down to a full turbulent cascade, and the energy travels down the cascade and dissipates to heat and acoustics. It's a beautiful process. Of course, it happens in submarines. These are just examples. Turbulence around submarines and their wakes and underwater and on their boundary layer. Of course, acoustics, and it's very important in those cases. Here's a stream. Anytime you go out and look at a river, you can see beautiful examples of laminar flow and turbulent flows all throughout the different flow field. Blood flow, of course, is another great example. Flow moves from left to right, laminar, and it might go into a little contraction and become turbulent, which is not ideal for blood in our bodies. You can also see turbulence in other beautiful parts of the world. You might look into an interstellar problem in the cosmos, and you might see fully turbulent flow and turbulence in so-called black hole radiation and fields. So actually, the turbulence in space of different quantities actually corresponds to Kolmogorov's theory too. There's actually composite profiles and breakdown with wave number to certain powers for different quantities. And these can be found following the methodology of Kolmogorov. they're interesting papers to read, and of course you can find them on Google Scholar. And of course, artists through the ages, from Da Vinci, which we showed in the beginning of this class, all the way to Vincent van Gogh can be shown here in his famous picture, Starry Night. And you can see, of course, the turbulence and swirls of the heavens. Next time, we'll talk about a little more prerequisites for turbulence. We will quickly review what we discussed today, but focus on critical issues to form the RAND space models of turbulence. We'll first have to define and describe the closure problem of turbulence. This means we have more equations than we have unknowns. This is due to the averaging technique. We'll look at Reynolds averaging, which we already discussed. But remember, Reynolds averaging is nothing but replacing the variables with their average, time average, or base value plus a perturbation. Of course, when we do this and insert them in the original equations, we'll have more equations than unknowns. We have to close these equations. This is the object of traditional turbulence modeling. And we'll find through this averaging process the so-called Reynolds stress equations and the Reynolds average Navier-Stokes equations. They're just a formation of Navier-Stokes equations. Then we'll talk about the different scales of turbulence, which we already alluded to today, and we'll talk about the so-called two-point correlations and related scales. These are going to be critical concepts before we move into the actual formation of the turbulence models, which of course are the actual equations which CFD codes solve for modeling turbulent flows. Thank you very much for your time today. I'm Professor Steve Miller.